This is problem 15 from Space-Time and General Relativity. Imagine that you and a friend are riding in trains that are moving relative to each other at relativistic speeds. As you pass each other, you both measure the time separation and spatial separation of two firecracker explosions that occur on the tracks between you. You find the firecracker explosions to be separated by 1 microsecond of time and 500 meters of distance in your frame. By radio, your friend reports that the explosions were separated by only 0.8 microseconds of time. Find the spatial separation of events in your friend's frame. So we have delta t for you is equal to 1 microsecond, and delta x for you is equal to 500 meters. You can call this delta r if you want to. I'm going to call it delta x, and then I'm going to say delta y and delta z are equal to 0, so our metric just becomes delta s squared is equal to c dt squared minus delta x squared. This is true for you, and it's also true for your friend. For your friend, delta t for your friend is equal to 0.8, 0 microseconds. Okay, so first we're going to look in your reference frame, and we're going to find the space-time interval. So this is equal to c times delta t for u squared minus delta x for u squared. So we have delta t in microseconds, and you can write the speed of light as 299.8 meters per microsecond, because if you have 10 to the negative 6th in the denominator, that's 10 to the 6th in the numerator, and it's 2.998 times 10 to the 8th, so if you move this over 2, then that gives you 2.998 times 10 to the 8th. So we have 299.8 meters per microsecond times 1 microsecond for u, and the microseconds cancel out, and we're squaring this and subtracting 500 meters squared. So 299.8 times 1 is just 299.8, and 299.8 squared is 89,880. And this is meters squared minus 500 meters squared. 500 squared would be 250,000 meters squared. And then if we take the difference, we get minus 160,120 if we round. So that is delta s squared, and if you take the square root, you would get delta s, but we don't need to find delta s. So we're going to leave it like that, and now we're going to say, for your friend, delta s squared is the same. Delta s squared should be the same for all observers in any reference frame. But this would be c times delta t for your friend squared minus delta x for your friend squared. And so I know what delta s is. And I know what delta t is for your friend, so I'm going to use this to solve for delta x for your friend. So this would be delta s squared is minus 160,120 meters squared. And then we have 299.8 meters per microsecond for C times delta t for your friend, which is 0.8 microseconds, minus delta x for your friend squared. So what is 299.8 times 0.8 squared? That gives us 57,523. And now we can solve this for delta x for your friend. So let's bring the 160,120 meters squared over to this side where it would be positive, and then we bring the negative delta x squared over to the other side, and we have 57523 plus 160120. This would have units of meters squared, and then we're taking the square root, and that gives us 466.5 meters. And let's just call that 400. No, we're going to call it 465.5 meters. This is delta x for your friend. This is what they asked us to find. And then let's just check the answer in the back of the book. So this would be answer number 1 at the end of this section, where D, which we call delta XF, is equal to 466 meters. So that looks good. And that concludes problem 15.